Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. To Madam Isadora binti Mustafa. We are from 3BRZ and today we are going to do a presentation for subject Digital Signal Processing under the title Design and Application of HANN and HANN Windowing Filters. So in here, we are going to talk about the HANN and HANN Windowing Filter. First, let me introduce to you our group members. Our group members consisting of 4 persons, which is Muhammad Adam Idham bin Muhammad Husni, Muhammad Adam Zafri bin Muhammad Hafiz, Lizzie, and Nur Fatiha binti Mustafa Kamal. All 4 of us will be presenting our finding on the design and applications of HANN and HANN windowing filters. First of all, I will start our presentation with an introduction. Signal processing is crucial in modern technologies, including telecommunications, audio processing, and scientific research. A major challenge arises when analyzing finite duration signal, often leading to edge effect and spectral leakage, which distort frequency domain analysis. Windowing functions, such as the HANN and HANN windows, are essential tools to mitigate this issue by tapering signal edges and reducing boundary discontinuities. For the key concept, spectral leakage happens when frequency component spread into neighboring frequency, causing a distortions. Windowing applies a smoothing function to signal to enhance spectral accuracy during frequency analysis, such as the fast Fourier transform FFT. So what's the difference between the HANN versus HANN windows? HANN window provide a balance between the main lobe resolutions and side lobe suppressions. It is ideal for application requiring moderate spectral resolutions, such as an audio processing. While a HANN window offers a superior side lobe suppression with a smoother transitions, it's suitable for tasks prioritizing spectral leakage control, such as a digital signal processing. Conclusions that we can get from the introduction is by combining a theoretical analysis and real-world demonstration. These studies underscore the significance of windowing function in improving the accuracy for reliability and frequency domain analysis in various signal processing tasks. An in-depth knowledge of windowing filters, specifically the HANN and HANN filters. So I will continue our presentations to explain the objective that focus on understanding the fundamental principle and characteristic of the HANN and HANN windows. It involves exploring the mathematical formulation behind this window, their impact on reducing spectral leakage in frequency domain analysis, and trade-off between frequency resolution, main lobe width, and spectral leakage, side lobe suppression. By gaining this knowledge, one can better evaluate the effectiveness and select the appropriate filter for a specific signal processing task. Second, for the HANN and HANN windowing filter to be designed, this involves the actual creation of the HANN and HANN window using mathematical expression and programming tools such as MATLAB and Python. The design process includes applying the formulas to generate the window shapes, and second, visualizing the time domain and frequency domain characteristics, and third, analyzing key metrics such as main lobe width and side lobe levels to understand their performance in suppressing spectral leakage. Third, to show real-world application of each and selected filters. This objective emphasizes demonstrating practical use cases where the HANN and HANN window excel. For example, HANN window is used in audio signal processing to achieve moderate spectral resolution. An example could be its application in speech analysis or sound equalization. For HANN window, used in scenario requiring strong spectral leakage suppressions, such as power spectral density estimation in scientific research or vibration analysis. By showcasing their real-world application, the importance of windowing function in practical scenarios becomes evident. Fourth, to have an engaging video that describes the theory behind the selected windowing filters. This objective aims to create a window that simplifies and visualizes the theoretical concept of windowing. The video shoots 1. Explain the problem of spectral leakage and how windowing addresses them. And 2. Provide intuitive visualizations of the Hamming and HANN window shapes. And 3. Highlight their performances differences with example of their impact on frequency domain analysis. So the goal is to make the subject engaging and accessible to a broad audience. And the last one, to present the use cases of the filters in practice and design process included in the video and the report. This objective ensure that the practical application and design methodologies for the Hamming and HANN windows are clearly documented and explained. Both of the video and the results should 1. Outline the step-by-step design of the filters. 2. Show practical use cases with relevant example and data sets. And 3. Compare the performance of the filters in different scenarios to highlight their strength and limitation. The combination of the reports and video ensure both theoretical and practical aspects are comprehensively covered and accessible in multiple formats.
Okay, for the next part, I want to show you for the simulation part. So basically, what we have in simulation, commonly we have flowchart and coding. Before we do the instruction code, we need to show the process of and the progression. Okay, firstly we need to set n equal to 1024 to initialize the number of points of frequency response to do a calculations, and then we need to define system for each filters. So we use 4 type of filter, which is low pass, high pass, band pass, and band stop. So for these 2 filter that we will show you the graph. And then for the next part, we need to set coefficient, which is we assign the numerator and denominator coefficients for each filter or transfer functions to do calculations. And then we calculate the frequency response for each filter, and then we calculate the zeros and poles and gain for each filter. And after we already calculate all this value, and then we use the subplot instructions to do a plotting graph, and the all value that we get will auto plot by the MATLAB. This is the coding that we do to get the graph, and I will explain line by line. So this is the system 1. We use low pass filter. Firstly, we need to declare the value for the coefficients, numerator and denominator for the transfer function. And then we declare the root function for the B1 and A1. And we use formula to do a transfer function for the low pass filter. And then we use subplotting instruction, which is subplot. Also for the label for the x-axis and y-axis. This is for method to respond. We need to use 2 subplot, which is for the method to respond and z-plan. So for system 2 is the same thing. We just change the value of the coefficient transfer function for the high pass filter, and then other than that we do something like the system 1. Same goes to system 3 and system 4. We do something, just the value of B3 and A3. We change the value and for the subplot and the others we do same thing because this is a same concept. So we move to for the result. Okay, so this is the result for the figure 1 that we not apply any window filter. So we can see the graph very not clear, and we cannot see the sine wave at all because there is no smoothing or tapering, and also its significant side lobes and irregularities. So it will make like this graph. So for the Z plane, the pole and zeros are directly placed without additional constraints, and the poles. So we can look at the poles close to the unit circle because of high gain, while zeros influence intonations in specific frequency bands. Then we go to the figure 2. Okay, this is a flowchart for the figure 2. A little bit difference from figure 1 because we just add cut-off frequency, only cut-off frequency for each filter. So, and the others is same thing, just same instructions. We need to design low pass filter, plot low pass magnitude and Z plane, and same goes to other filter. We do the same thing. Just the difference is we only define the cut-off frequency. So we look at the coding. So this is the coding. For the first part, we need to identify the number of frequency point, the filter length, and the sampling frequency to normalize the frequency. And then we define the cutoff, which is for the low pass, high pass, band pass, and band stop. And then we apply the hammering window filter for the instructions. And then we do a subplot instruction for the magnetic response and Z plan. For the high pass, is the same. Just change this line to the humming. Before this, for the figure 1, we don't use humming. We only put high only. So we just add humming to apply the filter, windowing filter. So for the band pass is same. Nothing different. Only change this part. This is the result for the figure 2. So we can see the difference the difference between figure 1 and figure 2 result. So we can see the figure 2 is clearly see the sine wave. In terms of shape, you can see the sine wave. Also for the other filter, it is after we apply the humming filter. So when we apply the humming filter, it will make the graph more smooth. It smooths the frequency response, reducing the side lobes. And then humming filter also can enhance attenuation in stop band compared to without use window filter. And then we also improve the transition region for the four filter. And then for the Z plane, we can look the poles and zeros is stable and maintaining, and also reducing the spectral leakage. And look at the circular, or we call as zeros. The circular cluster is more pronounced than unwindow case, which is there's a difference between without using window filter and use window filter. So when we use window filter, there is more cluster of circular at the Z plane. So we can assume the transition is smooth. It will make the transition is more smoother. This is the figure 2. The figure 3 and figure 2 flowchart is same, not different at all. Because the difference is at the design. Low pass filter is designed for the 4 filter, which we use to put just add to this line, which is HANN window filter. Before this, for the figure 2, we use hamming. For this part, we use HANN window filter. Just change for this part. Same same for the other filter. Only change for this to apply the filter. To apply the window filter. Sorry. And then for the subplot, also same. Firstly, we look at the declaration of the number of frequency, filter length and supply frequency is same, like figure 2. Also the cutoff frequency and the subplot, because the same concept. Okay, this is result for the HANN window filter. We can see the difference only at the Z plane, but for the magnetic response is same, nothing change. But this time we cannot see the difference, but there is different little bit with HANN window filter, which is there is more smoother transitions and better attenuations at higher frequency. There is difference, but we can see the difference because the graph looks same, but not. There is difference. Okay, for the Z plane, the result is improved for the stop band and reduce the ripple. It is a ripple in the pass band. The different. For the circular is more. The circular cluster is more better than the humming. So we can assume the transition is smooth. This is the comparison for the both window filters in terms of formula. This is formula for the humming window. We need to minus between 0.54 minus 0.46. And we need to multiply by cos and multiply by n minus 12 by n. For the HANN windows, we need to multiply between 0.5 and 1 plus cos multiply n minus 12 by n. For the purpose for arming windows is to reduce side loops in the frequency domain, and for the HANN windows to minimize side loops in the frequency domain but less aggressively. For the attenuation side loop, harming windows approximately is negative 41 dB. And for the HANN window, approximately negative 31 dB, which is less attenuation. For the amplitude, for the harming window is non-zero at edge. This is approximately 0.08, and for the HANN window is 0 at edges. For the visual shape, a small rounded shape with less taper at the edge. For the HANN window, has a smoother and more taper shape at the edges. So that's all for me. We go to the next part. So this is the application part for HANN and having Windows filter. This is coding for the having Windows filter. If you want to apply the Hammy Windows filter, we need to define the cutoff frequency. We need to normalize for each filter. So for the low pass for the low pass filter, we need to use the frequency below 0.2 to get the Nyquist frequency. And for the high pass, we need to use above 0.7 to get the Nyquist frequency. And then for the band pass, to allow the frequency, we need to specify between 0.3 and 0.6. And finally, for the band stop, to get the Nyquist frequency, we need to put the value between 0.2 and 0.5. We need to initialize for the four filter, and then we need to generate the input signal. This is the formula to generate the signal. And then for this part is we used to apply the humming Windows filter. So there is a formula that we need to put into the coding, and this is for plotting instruction for the subplot and title. Also for the X label for the X axis and Y label for the Y axis. This is for the magnetic response. We need to do for magnetic response and for filter signal. Sorry. So if you run the simulation, the graph will show two types of signal for the magnetic response and the filter signal for the each filter. Same goes to high pass, band pass, and band stop. There is the same instructions like low pass filter. Even we use the same instruction, we still get a different result. The result for the Hami Windows filter after we apply. So we can see for the low pass filter difference after we apply. We can see in theoretically there will less distortions, and for the high pass filter, if we apply the Hami Windows, less ripple frequency response, and for the band pass filter, will improve the sharpness of the band pass response, and for the band stop, will improve the performance by reducing the ripple in the stop band. Next, this is HANN window filter. So the difference for the coding, not too much. Just we change this part from humming to the HANN. because we need to apply HANN window filter. Just change to this part. And also for the other filter. That's it. Alright, this is a HANN window filter after we run the simulation. The effect after we apply the HANN Windows filter. The frequency response has a smoother transitions from pass band to the stop band compared to original one. And then the magnetic response will shows the gradual decline in the frequency response after the cutoff, which is typical of a well-designed low-pass filter. And then for the high pass, it helps to achieve smooth transitions between pass band and stop band. For the band pass, the effect for the HANN windows will minimizing leakage from a stop band into the pass band. And also will produce sharp transition for the specific frequency range. And then finally for the band stop filter, the effect after we apply the HANN windows, we will reduce the ripple in the stop band. Why we apply for this Windows filter first? Mostly we use the Harmony filter for the FIR filter design. The function for the Harmony Windows filter is to minimize the side lobes levels of the filter frequency response, and also will reduce the leakage effect. And then for the result, you will get the smooth transitions between pass band and the stop band for the filters. And then for the HANN window filter, we apply in FIR filter design. But this filter will improve the performance by improve the shaping the window to get more clear. And then the HANN window filter also can avoid significant distortion in the frequency response of the filter. So that's all for me for this part. We goes to the next part.
Good day, Kwan. My name is Lee Ji. For my part, I would like to discuss about the explanations of real-world applications. For humming window, since humming window is good in sharp filtering the noise and less noise considering, so it will be recommended using in the telecommunications, help design filters to reduce signal interface, making communication clearer. Speech processing using in voice recognition system to break speech into smaller parts for better analysis. Radar system improve object detections by reducing noise in radio signal. And the last one is for the power system, analysis power signal to detect problem like voltage fluctuations. And for hum window, comparing for the humming window, hum window has more smoother filtering compared to the humming window. So it will be recommended using in audio processing, using in music and sounds editing to make audio clearly and reduce noise. Another one is medical signal analysis heart like ECG or brain EEG signal to help doctors identify issues. Engineering, find vibrations or sound problem in machines or buildings. Frequency analysis help in tasks like earthquake monitoring by giving accurate frequency details.
Okay, this is my part about the conclusion for the assignment. So this project successfully achieved its objective by fully exploring the Hemming and hand window filters. Both filters we design and analyze to showcase the ability to minimize spectral leakage and enhance the enhance the representation of signal in the frequency domain. The study combined theoretical knowledge with practical example, emphasizing their significance in real-world signal processing application. So for the second point is, so throughout the project, the implementation of Hamming and HANN window across various filter types, low pass, high pass, band pass, and band stop was explored, shedding light on the distinct advantages. The Hamming window proved to be effective for tasks requiring sharper transition and moderate side load control, whereas the HANN window excelled in situation demanding smoother frequency response and reduce leakage. So the third point is the the accompanying video and detailed report provided an accessible and comprehensive overview of the design process, theory and practical use case of this filter. This combination allow readers and viewers to understand not only the importance of this windowing technique, but also how they can be applied in the digital signal processing. So the last point is in conclusion, uh, the project underscore the pivotal role of winnowing function in ensuring precise and reliable outcomes, reaffirming their importance in addressing modern signal processing challenge. So that's all from me, and then thank you. Assalamualaikum.